Hey everyone, we're going to continue chapter 14.4, part 2. So far, we have been talking about concentration and how does it relate for time. And today we're going to specifically focus on the part that talks about half-lives. First, we need to understand what is a half-life. The half-life of a reaction, which is commonly abbreviated T to the 1/2, indicating half, is the time required for the concentration of the reactant to reach half of its initial value. So if I'm starting with zero point 0.1 molarity, how much time does that take to cut in half? It's actually a very convenient way to describe how fast a reaction occurs, especially for first order processes or first order reactions. One thing to note is that a fast reaction is typically going to have a short half life. And what that means is it doesn't take that much time for the reaction to cut in half because it is happening so quickly. So we can actually use the integrated rate law and substitute things in for half-life in order to derive the half-life equation for a first order reaction. So the half-life equation for a first order reaction is down here in red. If you're going to rewrite it, you can write T 1/2 equals 0.693 divided by K. Again, T right here, 1/2 is the half-life. 0.693 is a constant that you guys get to keep. And then K, remember, is your rate constant. So one thing to note about this half-life is notice that the half-life of a first order reaction actually doesn't depend on your initial concentration at all. So it doesn't matter what you started with. The half-life is always going to be dependent on the K value. So determining the half-life of a first order reaction. Here we have a reaction and I stated that it is a first order reaction. And it says the initial concentration of C4H9Cl is 0.1 molarity. And it says the concentration dropped to 0.05 molarity. Notice here the concentration was cut in half. So that's why we're able to use the half-life equation. And it says that it takes about 340 seconds for this reaction to cut in half. And I have this in red because I need you to fix it in your notes. I'm determining the rate constant of the half-life. I did put in parentheses your K value, but I just really wanted to emphasize we are finding the rate constant in this problem. So here we're going to just go ahead and write out our equation. T of 1/2 equals 0.693 divided by K. And we just need to plug in what we know. Well, here we know that 0.693, and it's asking us to find our K value, so I'm going to plug in X there. Next, you need to figure out what T of 1/2 is. T of 1/2 is your half-life, and it's for time. So typically you're going to find a unit for time, and that's generally what goes there. So here, the time that it took for this to drop half of its molarity is 340 seconds. So we're just going to type in 340 seconds. Note here, this is just a label. You don't have to multiply it by 1/2 or anything. It's just a label. From here, it's a simple solve for x. I like to set things up as a proportion and cross multiply and divide. So that's what I'm going to do. So here, if I set it up as a proportion, I have 0.693 equals 340x. I'm going to divide by 340 to get x by itself. And we're going to get x equals 0.002038, etc. And since I am going to round to 2 sig figs, 0.0020. And then we have to come up with a unit. Now, this is a first order reaction, and I'm looking for rate constant. So you should recognize that your first order reaction rate constants are always the time to the negative first. Here, my time is seconds to the negative first. Here I have another example of a half-life reaction, but instead of finding rate constant, we're actually going to find the half-life. So again, it says the initial concentration is 0.1 molarity. The rate constant for this reaction is 0.14 seconds to the negative first power, and it's asking us to find the half-life. So remember, our equation is T of 1/2 equals 0.693 divided by K. It's asking us to find the half-life, so that's going to be my X value, my 693, and then I have to figure out what my K is. Remember, K is rate constant. So here it says my rate constant is 0.14. Here you can just plug that into your calculator. And when you plug that into your calculator, you're going to get a long decimal, which, well, actually not that long of a decimal. You're going to get X equals 4.95. Because I do want only 2 sig figs in this problem, that 5 rounds that 9 up to a 0, so X equals 5.0. And then I need a label. Here, since I'm finding half-life has to do with your time. So my time in here was seconds. So here it's going to be seconds. It takes about 5 seconds for this reaction to be halfway done or cut the reactants in half. Just like we did with the other ones, we're also going to learn the half-life of a second order reaction. The half-life for a second order reaction and other reactions depends on the reactant concentrations that you start with. And therefore, it's going to change how the reaction progresses. In other words, having more concentration or less concentration. We can actually determine the half-life of a second order reaction, again, by substituting these values in. When we substitute these values in, it's already bolded in red what I will give you on your test. Your half-life for a second order reaction actually equals 1 divided by your rate constant, which is K, times your initial concentration, which is A to the 0. One thing I also want you to know is that with second order reactions, typically the lower the initial concentration, that means the longer the half-life. Remember, if it's long, that means you have a high time. So, high time number. So again, lower means you have a higher unit for time. This is an inverse relationship. So a second order reaction has a half-life of 18 seconds. When the initial concentration of reactant is 0.71 molarity, the rate constant for this reaction is blank. So here we're trying to solve for the rate constant, and so we need to bring up that equation again. Remember, a second order rate equation is T 1/2 is my half-life equals 1 divided by my K times my initial concentration. I just need to plug in what I know. So here I know my half-life is 18 seconds, so we're going to plug in 18 seconds here. This is all going to equal 1 divided by, here it's asking for K. I don't know K, so we're going to plug in X for that. And then here A, concentration of A to the 0 is my initial concentration. So my initial concentration was 0.71. I'm a really big fan of proportions, so I'm just going to go ahead and solve for X to get it by itself as a proportion. So here, 1 times 1 is 1. 18 times X times 0.71 actually gets me equals 12.78X. And then in order to get X by itself, we're going to divide by 12.78. And then here, X is going to equal 0.07824722613. Because I want to round to 2 sig figs, I'm going to say 0.078, and then I need a unit. It is asking for a rate constant, and so it's going to be dependent that I am on my second order reaction. Remember, the rate constant of a second order reaction is m to the negative first, s to the negative first. Here is another example where we use a second order half-life, but instead of solving for our rate constant, we're going to actually solve for the half-life. Again, I'm going to start this by writing the equation. T of 1/2 equals 1 divided by K, and then my value of A to the initial concentration. So here, when you go and solve this, we're going to read this problem and plug in what we have. So here it says, for the second, the rate constant at 501 Kelvin, so that's temperature, that's not my rate constant, that's just temperature. My rate constant is actually 7.93 times 10 to the negative third. So I need to plug that in for K. So I'm going to do 1 divided by, and let's plug that number in for K, 7.93 times 10 to the negative third. And then it says my reaction half-life at this temperature, when the concentration of nitrogen dioxide is at 0, is 0.45 molarity. So that's my initial concentration. So 0.45, since it's molarity, again, that's my initial concentration. And it wants me to calculate the half-life, because it says the half-life when that concentration is this is blank. So that's what I'm trying to find, is half-life. Here, you can just plug this into your calculator. Make sure you you multiply the bottom and get those figures together, and then 1 divided by the number. When you plug that into your calculator, you get 280.2297884. Again, I only want 2 sig figs, so 280 without a decimal seconds counts. The zeros at the end and there's no decimal, so it would not count towards my sig figs. So 280 seconds. And what this means is it takes 280 seconds for 0.45 concentration to be able to be cut in half. The last one is the half-life of a zero order reaction. The equation for this one as follows, if we substitute everything in, is T of 1/2, which is your half-life, equals your initial concentration divided by 2 times your rate constant. Here, one thing to note is that the lower the initial concentration, the actual faster the half-life. So here you have a low concentration. So if you're faster, you're going to have a low time. So lower, this is a direct relationship. So if I have the problem, if substance A is a zero order reaction, has an original concentration of 1.2 molarity and a rate constant of 0.00624 molarity per second, what is the half-life of substance A? Like I said, I always begin every problem by making sure I understand what the equation is. So my half-life is actually equal to my initial concentration divided by 2K. Let's plug in what we know. It says my original concentration is 1.2, so we're going to plug in 1.2. Then it says my rate constant is 0.00624, so that's my K value, and I need to multiply it by 2. So 2 times my K value, 0.00624. And this is all going to equal my half-life, which is what it's asking for me to find. Here, we're going to combine like terms, 2 times my rate constant, and then I can take 1.2 divided by whatever number I get, and you should get x equals 96.15384615. Again, I want to round to 2 sig figs, so x equals 96. Since it is asking for the half-life, and remember this is molarity per second here my thing is going to be seconds. So it takes approximately 96 seconds for 1.2 molarity to be cut in half. And that's the end of today's lesson. Let me know if you have any questions, and I hope you guys have a great day.